Good morning, good afternoon, good evening, depends on where you are. Welcome to the Design Automation webinar, DOM. Okay, so this is the first DOM in this year. Actually, we actually held many DOM webinar 2 years ago. So this year we will start to reinitiate the DOM webinar. Okay. So the topic for today is the best of EDA research in 2021. So this DOM webinar is organized by Dr. Yuanhao Zhang from Academia Sinica and me, and with the support from the ACM6DA and the IEEE TCAD and Synopsys. Okay. So the topic, the best of research in EDA in 2021 is that we select the best paper award winners. Okay, in these very important journals and conference in EDA from IEEE TCAD, DAC, ICCAD, DAC, ASP-DAC, and ESWEEK. Of course, the very important conference in micro. Okay, so we totally select 8 papers. The authors of these 8 papers will make presentation in today and tomorrow. Okay, so the fashion will be like this. We will have so today we will have 4 papers. Okay, the first one will be start at 10 a.m. and Eastern time. Okay, so the first paper is from TCAD. The second paper is from ICCAD. The third one is from micro. The last one will be from DAC. Okay, that's for today's section. Okay, for tomorrow will be papers from TCAD, ASP-DAC, ESWEEK, and DAC. Okay, so for today's session, most of papers are related to architectural search and also microarchitecture. Okay, and tomorrow we will have more papers related to EDA and also the embedded system. Okay, so I think the purpose to hold this DOM webinar is because in last year, I think currently, because due to the weird COVID pandemic, so we cannot attend the conference in person. Okay, so most of the conference are actually held in online mode or either for hybrid mode. So due to the different time zone, people cannot attend all the sections, and not to mention asking questions. So now we invite the authors of this best paper award winners to join this DOM section. So I hope everyone can enjoy. Okay, so let me introduce the first speaker. Okay, the first speakers. Let me stop the sharing. Okay. So Weiwen, you can share your screen. Yes,
sure.
Please. Okay. Yeah. Okay, so the first speaker is from the actually Professor Weiwen Jiang from the George Mason University. He is currently an assistant professor of EC department there. He was a postdoctoral associate at the University of Notre Dame, and he received a PhD degree from the Chongqing University. And before that, he was a research scholar at the University of Pittsburgh. Okay, his research work not only received the Best Paper Award in TCAD, he also received the Best Paper Award in ICCAD and NVMSA. Okay, and his recent work on the quantum, he developed the co-design framework called the quantum flow to demonstrate the quantum advantage in design neural network on a quantum computer. So this work was published in Nature Communication, a very important journal. Okay, so Weiwen, now the time is all yours, please.
Thanks, Song-Yi, for the kind introduction. Hello, everyone. I'm very glad to be here to present our research hardware and software co-exploration of new architectures. Actually, this work was conducted by my wife Jiang and also me when we was a research scholar and Professor Jintong Hu's group at the University of Pittsburgh, and also when we were the postdoc associate at the Professor Yi Yu's group at the University of Notre Dame. By the way, I list the website of my group here, and the slides for today's presentation will be available there. Okay, so let's start this presentation. So as everyone knows, that the AI is growing to be everywhere in our computing system, and also for different applications like the agriculture, the military, and so on. And when we moved to a specific application, actually we also we still have the bottleneck in applying the machine learning for these applications. So in this slide, I demonstrated that when we target the very traditional machine learning task, that is the image classification, we have the data set like the ImageNet, everyone use it. And the task here is that we want to classify the input image to a class like the ski for this one. And also the box here is the machine learning algorithms, and all of us know that the very important component in such kind of framework will be the neural network. However, the design of neural network itself is not for free. Actually, it has very high costs. And demonstrated in this slides, actually, if we want to manually design the neural network, it requires expertise from different domains like the computer vision, computer science, and also data science. And if we move to other application like the medical application, we also need the expertise from doctors. So fundamentally, actually, we need the collaboration of the experts from different domains, and you know that this is a very difficult task. In addition to that, it also involves large human labor and also have a very long launch time. So in order to address such kind of problem, the auto machine learning, the auto ML is a promising solution. So in this scenario, in addition to manually design the neural network, actually we will replace the experts by using the automated optimization approaches like the reinforcement learning, like the meta heuristic, like the gradient descent based optimizations. So we can release the labor from experts and also shorten the launch time. So here I use the reinforcement learning as an example to demonstrate how such kind of things can work. So we will regard the neural network space as an environment, and for each time, the agent, our optimization controller will predict, will short an action, and then it will affect the environment. Then we can obtain the accuracy, and the accuracy will be a reward to update our agent. So such kind of by using such kind of optimization loop, actually we can iteratively optimize the circuit, the neural network. That is, we can design the neural network. So the reward here is a key component because it is related to our objective. If we want to maximize the machine learning performance, we can set it as the prediction accuracy. So then at the end of the day, we are expected to have a neural network has a high accuracy. Now it seems very good because we can we are no longer need the experts to design the neural network, but the problem also exists, still exists. The problem here is that for today's new machine learning, actually we need to run the machine learning algorithms on the hardware platform. As demonstrating here, we show three very popular platforms. The first one is for the cloud and the high performance computing platform. And the platform itself has the property with unlimited resources. So the objective here is only accuracy. Based on such kind of rule, and the second platform we demonstrate here is a mobile phone. It represents a set of hardware that is for the edge computing, and the property of such kind of computing resources is that it has the fixed hardware. So then in addition to that, it has very limited hardware resources. So that we are not only want to maximize the accuracy, but we also want to minimize the latency. Based on such kind of things, the mobile net and also FBNet and the Praxis net NAS were proposed. And move forward, actually, we have the programmable hardware like the FPGA, and also we have the design of other hardware like the ASIC computing in memory architectures. So for such kind of hardware accelerators, actually, we further have the hardware design flexibilities, and we expect to have a more energy efficient solution. So that we are not only consider the latency, but we also want to maximize the energy efficiency, such kind of thing. And based on this, different neural network were also proposed. So now it is very clear for us. So for such kind of problem, we are given the data set, we are given the hardware platform. The problem we are going to solve is that we want to find a neural network. In this slide, in this shape, actually each dot present a potential neural network, a possible neural network architecture. So the task for us is that we want to find a neural network architecture that can maximize both the software performance and something like the accuracy for the classification task. And also we want to maximize the hardware performance for FPGA, like the energy efficiency or the pipeline efficiency. So in the following, actually, I would like to first give a quick overview of the road from the manual design to the auto machine learning, and then I will introduce the hardware and the software core exploration framework proposed by our TCAD paper, and followed by this, I will show some our most recent works and also give the conclusion of this talk. Okay. So in this slide, we will show the road from manual design to the automated co-exploration in the past 10 years. In the right bottom column, actually, we demonstrate the different hardware platforms, but at the early stage of our neural network design, actually, the people only targeted the cloud computing or the high performance computing without computation resource limitations. Based on such kind of thing, we have the ANXNet that is very famous. We have VGGNet, GoogleNet, ZFNet, a lot of manual design network. The problem here is that the cost is very high, as we have already stated. And in addition to address such kind of problem, the new architecture search was proposed by Google in 2016. It formulated such kind of reinforcement learning optimization loop, and a controller which is also the recurrent neural network will guide the optimization loop. And then it will identify one neural network, a set of child networks, and obtain the accuracy. By using this accuracy, it will update the controller to better optimize the new architecture exploration. And for such kind of thing, such kind of work, the one of major bottleneck is that it has very high search cost. So that the DAC, the differentiable architecture search, were proposed in 2018. And also another limitation is that it only targeted on the cloud computing without computing resource limitation. When we moved to the edge device, like the mobile phone, like the MCU, actually we have further problems emerging. So in 2018, actually the MNASnet also from Google were proposed. So it will target a fixed hardware platform like the mobile phone. After identify the new architecture, it will go through the hardware to predict its hardware efficiency, and then it will use the accuracy and the timing, the latency together to update the controller. So such kind of thing can also be, the efficiency can also be improved. So the differentiable approach-based proxyless and FBNet were proposed, and also people will apply such kind of approach to the microcontroller. And after that, we have the, we are thinking about if we moved to the FPGA, the program, the hardware itself can be programmable. Whether the existing approach for the hardware-aware new architecture search can also be applied. And also, we found that there is some challenges in such kind of scenario. And as shown in this slide, in addition to have a fixed hardware, actually we further have the hardware design space, so that we need to not only optimize the architecture search space at this moment, but we also need to involve the hardware design space. And in our FNAS work and this TCAD work, actually we propose the framework to support such kind of thing. And the related work is also conducted by the researcher from the UIUC and Samsung. And after that, we also propose the framework for different computing platform like the ASIC and also computing memory architectures. So this is an overview of the road from the manual design to the auto ML. So the next part, I will introduce the hardware and the software co-exploration framework. The first thing I want to mention is what's the motivation to conduct the co-exploration, to conduct the co-design for the neural network system design. And here we use an example based on the CIFAR10 and the Xilinx FPGA, and we applied the existing approach, hardware awareness, and also we apply another approach to do some sequential optimization. So let's first say the hardware awareness. So for such kind of thing, as we introduced, we will have a fixed hardware. That is, we are going to find the neural network N under the fixed hardware H, so that we can maximize the accuracy and also satisfy some constraint on the hardware performance. So for here, we highlight the N out because we only have the ability to identify the architecture of the N. We only have the ability to search the search space related to the neural network. And we are thinking about this problem after we have the neural network, whether we can further optimize the hardware for a better performance. And we conduct such kind of sequential optimization. So for the first step, we conduct the hardware awareness, and the second step, we optimize the hardware for the neural network. And we obtain the better result because we are based on the same approach to obtain the N, so the accuracy will be the same. But after we do the further optimization on the hardware, we can observe that we can have higher throughput and also higher energy efficiency. So this observation gave us the hint that the hardware and the network optimization are coupled with each other. So in order to achieve the best performance, actually we need to optimize or search for both search space so that we can identify the best architecture. So whether the sequential optimization is the best solution, and after that, we are thinking about whether we can do the co-exploration so that we can optimize the hardware and the software in a holistic optimization loop. And we conduct some experiments based on the data set and the Xilinx FPGA board, and we observe that by using such kind of co-exploration, we can further improve the accuracy, and also we can significantly improve the hardware efficiency on both throughput and energy efficiency. So this gave us a motivation. We need to do the co-exploration. But the problem here is that how can we conduct the co-exploration? And we propose the framework in the TCAD paper to do such kind of optimization. After years of study on the auto machine learning, it gradually becomes clear that in order to conduct the automatic optimization, we need 3 components: the optimization controller, the search space, and also the evaluator. In the previous work, actually, people will only consider the hardware software in the search space, but in our work, we bring the hardware design space in the search space as well. So in the optimization loop, actually, the controller will iteratively select the solution from the search space for the evaluation, and then the controller will be updated by using the result from the evaluator. So this is for the whole loop for the optimization. Next, we will see the details of each component. So for the controller here, we use the reinforcement learning, the very standard reinforcement learning to conduct the optimization, but you can also replace this part by using other optimization techniques like the meta heuristics. And for the search space, we consider the new network hyperparameters, the neural network hyperparameters for the software side. And after we identify the child network, we will partition and assign the subtask to multiple FPGA. So in this paper, we consider the multiple FPGA system so that we can formulate a pipeline of execution. And the hardware performance we apply here is the hardware utilization. We want to maximize the utilization. And at this step, because we will only target the utilization optimization, so that it is very fast, we will not go through detail for the training of the neural network. So we call the first level of optimization as a fast exploration. After that, we have the evaluator to obtain the accuracy by training the neural network, and also by using the utilization obtained from the previous level. Actually, we can generate the final reward to get, by using both the accuracy A and also the utilization U. After that, we have the full picture of the framework to conduct the co-exploration to search the hardware and the software at the same time. Okay, the next page, actually, I will demonstrate some result from our paper. And in this slide, we compared the hardware efficiency on the y-axis and the accuracy on the x-axis. And each point here will be a potential solution for the pair of hardware and the software. And the green lines represent the solution is explored by the existing hardware aware new architecture search, and the red line represents the solution obtained by our approach. And on the left hand figure, actually it is the solution targeted on the system with at most 2 FPGAs, and on the right hand side it is the solution for 3 FPGAs. For both cases, actually, it is clear for us that the parameter frontier between the accuracy and the hardware efficiency can be significantly pushed forward. Another interesting result from this paper is that people will think when we target on the hardware, whether we can directly use the model size to constrain or to represent the hardware efficiency. But in this figure, we demonstrate that for this metric considered in this paper, that is the hardware utilization pipeline efficiency, actually larger model size may bring higher hardware efficiency. So simply minimize the model size may not work for such kind of scenario. And we also conducted the experiment on different data sets like the CFA10 and ImageNet. Actually, we achieve the similar result that our proposed approach can outweigh the existing hardware awareness and the sequential optimization. Finally, I will simply go through the follow-up works so that you can have a better understanding. This will be the fundamentals of the presented work is the fundamentals of many other directions. And okay, so this team built up the design stack and for the hardware and the software co-design, and also most recently we also applied the co-design philosophy to the quantum machine learning. So for the hardware and the software co-design, as you can see, the kernel part will be the co-design framework proposed by this paper. And on top of that, actually, we have the optimization on the hardware side, on the application side, and also in the middle layer, the algorithm optimization. And our initial work obtained the best paper award and TCAD, and also best paper nomination and the DAC in 2019. And for our hardware exploration, we have we conduct research on the FPGA and the ASIC. These two works obtained the best paper nomination and the ESWEEK and the ASP-DAC. And we also conducted some very initial results for the computing in memory architecture search. And for the algorithm side, we consider how can we accelerate the new architecture search process and also do the model comparison and the secure inference. And finally, when we move to today's machine learning system, we are thinking about that we are not only need to provide the hardware platform, we also need to apply the co-design framework to the application, so that we do a lot of exploration on different applications, from the medical image to the natural language processing, and also the graph-based new architectures. And so for here, we demonstrated our initial work on the FPGA design. We deployed the neural network on the multiple FPGAs, as shown in this slide. In the next work, we conducted the very first hardware software co-design work for the ASICs that has very huge hardware design space. And this work was published in the DAC in 2020. And after that, we also explore the co-design for the computing in memory architecture. And you know that for the NAS, the search time is a bottleneck, and also and in 2020 CODES conference, actually we proposed the hot NAS to reduce the search time from more than 200 GPU hours to 3 GPU hours on the ImageNet dataset. And finally, the last work, this is the most recent work. Actually, the work has been accepted by DAC this year, and we observe when we applied the co-design philosophy to the application, to the specific application like the medical image, it has a new problem like the fairness in the medical images, and we proposed the very first framework to consider the fairness issue together with the new architectures. So we formulated such kind of design stack, and a lot of publication can be found in my lab's website. And finally, a quick concluding. So this work provides the very first framework to conduct hardware and software co-exploration. And we demonstrated that the co-exploration can push forward the painful frontier between accuracy and efficiency. And also this work provides the fundamentals of the code design stack. And in our most recent work, we even apply the code design philosophy to the quantum machine learning, so that we can achieve quantum advantage. And this work was published in Nature Communications. And here is a list of reference. And thank you so much for your attention.
Okay. Thank you, Weiwen. Wow, that's a very comprehensive. Wow, you already prepared several follow-up work, and also you also provide several group of continued research for this direction. I think it's really good. So actually, you already answer most of the questions for the audience. Yeah, because I think many audience may be very interested about some follow-up work for your research. Okay.
Sure.
Yeah. Great. Thank you. So I think we have two quick questions. I think when you can answer these two. Can you answer these two questions?
Sure.
Yeah, from the chat box. Yeah.
Okay, so what does hardware aware stand for? So actually, when we consider the computing platform, actually you can divide the computing platform into groups. The first one is the general purpose computing resources like the CPU, GPU. Actually, the hardware aware is for this group of the computing platform. And on the other side, we have the FPGAs, ASICs, and all of this stuff we need to not only do some programming and launch it on the general purpose computing, but we also need to design the hardware. So this is the difference between the hardware aware neural architecture search and the hardware and the software co-design of neural architectures. And the second question is, it seems that you are optimizing a neural network platform with another neural network platform. Which platform do you apply for quantum machine learning to? Okay, for the quantum machine learning, actually we will target on the quantum computers, and actually so that is a totally different story. And if you have interest, I refer you to see our recent publication on the quantum machine learning work. And I think there is another question about compare with AutoML. Do you think a hand-designed accelerator for CNNs has any advantage? Yes, actually, I do believe the hand-designed convolutional neural network or deep neural networks provide a lot of insight to help the auto machine learning. I do believe they are also valuable, and because for the AutoML we have the search space. A lot of search space is designed based on the existing the design that is explored by the manual design. So then if we have some innovation and novelty in the manual design, and we can integrate it to the search space, that will help. That will be a great help for the auto machine learning. So I think this is my answer for this question. Hope you think that will be useful.